Alright, welcome to another AQA A-level chemistry video. This is a continuation from the part 1 video on commercial application. So this is just me. I decided to really to make this a 3-part video, where part 2 and 3 just me going through exam style questions. I know, especially this time right now, there's a massive emphasis on, as we're getting closer to the exams, on exam style questions. So I really want to emphasize on exam style questions and the content that's really important that's related to those exam style questions. Because as I said before, knowing the content is useless really, in my opinion. It's about how you answer the questions. That's just the way it is. You need to be able to understand how to answer the questions more than just saying I understood the content really. Because they judge you on how good you are understanding the content by how good you are by answering the questions. As I said before, I don't really necessarily agree on that being the best method, but it doesn't really matter. That's what we're doing here. And this video, I'll be going through some exam style questions. I'll allow you to answer those questions first, and then I'll go through them, and then I'll go through the mark scheme of them. And then after that, the part 3 is me going through the rest of them. I decided to make this a part 2 and part 3 because I've got quite a few exam style questions, and I didn't want to bore you guys by making like an hour-long video. I decided to do a 24-ish. This video will probably be like close to half an hour, hopefully. And that's with me going through the exam style question, as in me going through exam style question and then going through the mark scheme, looking at make sure that I've corrected it. And yeah, but before I actually do that, I want to make a quick adjustment and say that I wasn't able to find this last time. I wanted to include it. And just a bit of backstory in the Daniel cell. You don't need to understand this. It's just a bit of backstory to get you a bit of a grasp onto what the Daniel cell is. I already kind of talked about it in a previous video, so I'll leave a link into that video. And the Daniel cell is a type of electrochemical cell invented in 1836 by John Frederick Daniel, hence the name Daniel. And he was a British chemist and meteorologist, and consists of a copper pot filled with a copper 2 sulfate solution, in which is immersed an unglazed, unearthen container, which I assume is just what the porous cup is, right? Which is acting as a salt bridge. And that's filled with the sulfuric acid and a zinc electrode. And I got that information from Wikipedia. So just a bit of information. So the copper pot is just acting as your anode, and your zinc is acting as your cathode. And that's it. And I've got a couple of exam style questions on the Daniel cell, because I think it's quite important to understand that, as I said in my previous video, the Daniel cell, you just treat that like any other type of electrode potential, or any type of electrode, half cell or cell, right? And you just treat it like this example here. Don't get twisted thinking some completely different thing. It's the same principle, it just looks different, but it's the same thing. Accomplishes the same goal at least. Yeah, but it's not gonna be in this. It's not gonna be in this video. That'll probably be in the next video. But I'm gonna get this done now. So, I've got a 24 marker, right? I'm gonna allow you to look through them. Well, I'll scroll down so you can see every single question, and I'll go through them. And once I've and that's up until here. That's it. And then after that, first of all, I need to now go and pause the video. I'll try, and then once I've done that, once you've answered the questions, really, I want to try and do it in 20, or it was 24, it's 24 marks, so 24 minutes. I'll set a timer here. I might not complete it in the 24 minutes exactly, because I'm going to be talking through it. But just know that you should be able to do this within 24 minutes. I'll put time on my watch as well, so I can keep it up here as well. And then, yeah, let's go for it. So, diagram represents the cell used to measure the standard electric potential for Fe3 plus Fe2 plus electrode. Name piece of apparatus is labeled A, salt bridge. State the purpose of A. So the salt bridges allow free movement of ions between the cells, between the half cells, through the salt bridge. Name the substance used as electrode B in the diagram above. It would be platinum because we're not forming, that's the Fe3 plus the Fe2 plus electrode, and we're not forming, we're not change, there's no change of state, which it's just, it's still remaining as a solution here. So it would be platinum, and platinum, as I said before, is a perfect conductor of electricity, so we can use that for that type of reduction, but it's inert, so it won't react with the platinum, with the iron, sorry, the ion. Complete table 1 to identify C, D, and E from the diagram above. Include the essential conditions for each. So C is, well, that's just going to be a strong acid. I can use HCl. It's because HCl is a strong acid that associates 1 H plus, so we can use 1 mole per dm cubed. But if I was using, I could use H2SO4, but I could use H2SO4, but it'd have to be 0.5 moles per dm cubed, which you could also do. D is H2 gas. Also have to use the state symbols here. Aqueous. H2 gas, and that's at 100 kilopascals of pressure at 298 Kelvin. E, well, it's 1 mole per dm cubed of it. Make that 1 mole per dm cubed, and then well, the solution. Well, we could use FeSO4, Fe2S. No, technically no. You can get away with just saying Fe3 plus, because remember they will all dissociate down to Fe3 plus and Fe2 plus anyway. They'll allow a solution of Fe3 plus aqueous and Fe2 plus. And it'll be 1 more. The standard electron potential for the Fe3 plus Fe2 plus electrodes is 0.77 or plus 0.77. Give the ionic equation for the overall reaction in the cell in the diagram above, and then state the change that needs to be made to the apparatus in the diagram to allow the cell reaction to go to completion. So give the ionic equation for the overall reaction in the cell diagram of the ionic equation. This is standard hydrogen electrode, so it's always talking about the reduction of Fe3 plus anyway. But anyway, the standard hydrogen electron is always going to be 0 electron potential. That's it. What am I talking about? This is the standard electron potential of Fe3 plus. It's always going to be Fe3 plus. Is always going to be reduced. So Fe3 plus an electron goes to form Fe2 plus. But I have, so that means that iron 3 plus is going to get reduced. So hydrogen is going to get oxidized to 2H plus 2 electrons. Going to there's 2 electrons here, times this by 2, right? So we have 2Fe3 plus aqueous plus H2 gas goes to form 2Fe2 plus 2H plus, and then the electrons will just cancel each other out. State the change that needs to be made to the apparatus in the diagram to allow the cell reaction to go to completion. We need an appliance in order to use those electrons, and that would allow the continuous reaction to occur until completion. So we can exchange the voltmeter for some sort of appliance, like a bulb, right? Or lamp, I should say. That's the scientific term for it. So remove, or say, replace the lamp, replace the voltmeter with a lamp. We could use any other type of appliance though. The easiest one I can know. Everyone knows what a lamp's with a lamp, and that's going to be using up electrons. That's going to make the reaction go to completion. Anyway, students sets up a cell shown in the cell representation here. Okay, student measures the. By the way, I'm assuming you've looked at these questions and tried to answer them. That's why I'm just going through them. Student measures the EMF, 7 different concentrations of CO2. Complete table 2 to show the value missing from experiment 4. Okay, now I'm just looking at what the thing's trying to what it's trying to tell me. It's trying to say learn of well, concentration of Zn2 plus, which is 1 over concentration of Cu2 plus, which is 0.1, and then that is 2.3, round to 2.3. I can see a trend here, right? And then they want me to plot a graph of electrical again. Okay. What's okay? Wait. That's negative. So then, no, this is negative. So Lun is negative. So that's, and then that's going from 1 point. Okay. Okay. I'll get my ruler out. I believe that is the dead center. Looks like it at least. And what's going from 1 to 5 really? So 1, 2, 3, 4, 5, -1, -2, -3, -4, and -5. You don't have to do every single one, but just because I can really. And then going up, drawing out this graph is going to be 4, 2, 4, 6. Where I just do start from 5, 6. No, I'm going to have to start from, you can do this. I have to start my graph from 1.04. 1.04, 1.06, 1.08, 1.1, 1.12, 1.1, 1.14, and 1.16. Now I have to go and put this into our graph here now. So minus 4.61 is 1.16. So minus 4.61 to, yep, minus 2.3, that's 1.13. So minus 2.3, what's that, 1.13, 1.13. That 1.1 is 0, so that's fine. That's dead on there. I do this like everybody's going to be doing this on iPad now. You're going to be doing this on paper, but try not to scribble over the dot if you the X if you make a mistake there. 2.3 and 1.2. Wait. Yeah, 2.03. So 2.30 and 1.07. And then the last one is 4.61 and 1.04. So 4.61. Okay. My ruler is a bit mashed up, so use a proper ruler in your real exam. But I'm using my ruler right now. This equation shows the electric cell potential varies with concentration of this reaction. This equation is in the form of straight line y equals mx plus c. So this is y mx c. Calculate the gradient of your plotted line graph f. You must show your working. So I will use. I'll use just these two. So 1.07 minus 1.1. 1.07 minus 1. It's always rise over run. Why can't I move my... Okay. Do we do me like this? 12 minutes. My thing's just kind of frozen here. Sorry, let me just pause this for a second. And my screen's just kind of frozen here. Yeah, sorry. I'll continue the timer here. Resume. (1.07 minus 1.1) rise over run. And also you have to show with your thing, with your where on your, if you're using that, you got to show where you've used it from. So 1.1 and 1.07, right? And it's this here, isn't it? So showing with a triangle where you're taking gradient from. And that's what's again? 2.3 minus 0. Zero is just 0.03 minus 0.03 in there, but anyway. And it is equal to 0.13, minus 0.013, minus 0.013. Use a gradient to calculate the temperature T at which the measure. Wait, so sorry, it may look like this is a two-part question. Really, it's just there's a massive gap here for some reason. Anyway, minus 0.013. That's from the previous question there, and then use a gradient to calculate temperature T at which the measurement. So then, okay, this is a good indication because if your answer is close to this, so occasionally if you're unable to calculate gradient, they'll tell you to use this one here, but we've obviously done it correctly. But this is actually quite good because I never say, it's not reliable to say this, but if your answer is close to this, usually in exam, it means you're on the right track. It means that this one is usually correct. But don't take it for don't mean that it's correct all the time. But in my experience, usually it's a good sign. Anyway, I'll continue this. So we know that M is equal to minus 4.3 times by 10 to the power of minus 5 multiplied by T. Right, when we get T, we already have M, so T is just equal to minus 4.3, no, T is equal to M over, so minus 0.013 over minus 4.3 times 10 to the power of minus 5. T is equal to, put that into a calculator, answer over minus 4.3 times 10 to the power of minus 5. I got 303.3. 303.3. But really just they want it to two significant figures, is it? Two significant figures, so I just leave that as 303 Kelvin. Experiment table 2, the electrode potential of Cu2 plus electrode is 0.33 volts. Use data in table 2 to calculate electrode potential for the Zn2 plus electrode in experiment 2. Give a reason for your calculated value in different. Give one reason why your calculated value is different from the standard electrode potential. Okay, so that's what I'll go work out what the electrode potential is. So working out the electrode potential for Zn2 plus, but then which one is the cathode and which one's doing reduction, which one's more doing oxidation. So you know this is Cu2 plus is 0.33, but actually no, we can look back at our equation. So we know that Cu2 plus is the one that's doing oxidation, right? So that's going to be the one that's going to be taking away from. So it's, if you want to work out Zn2 plus, that's the one that's going to, so this 0.33 is the one we're going to be taking away. So we're going to be doing, it's technically X, because that's when Zn2 plus has the higher electric potential, or it's the one that's being reduced based off of our, we know that this is the conventional representation, that's one being reduced, so that's going to be X minus 0.33 is equal to, they told us at one point, didn't they? Oh, C. The C-intercept is the electrode potential here. So 1.1 equals 1.1. So x is just equal to 1.1 plus 0.33, which is equal to 1.43. Yes. Given reason why I can't devise difference and because it's probably not under standard conditions, is it? Yeah, it's not under standard conditions of 1 mole per dm cubed as seen right there. So the concentration of Zn2 plus isn't under standard conditions. Of 1 mole per dm cubed. Time of I've got 6 minutes 50 or 7 minutes to do this, right? Yeah, that sounds right. Good, you find that. So 7 minutes to that. Shouldn't record it. Shouldn't record it. By the way, I'm assuming you've already looked and read over this and you're just doing it right now. I assume that you answer these questions already, as I said by the start. Explain how the salt bridge provides an electrical connection between the two solutions. All right, so it allows for the movement of ions. I never like using the word it, but I'm going to mention salt bridge anyway. It allows for the movement of ions between the half cells through the salt bridge. Should I say to maintain charge balance? I'll leave it there if I have time at the end, but it's not really necessary right now. Standard electric potential for the Cu2 plus Cu electrode is that, and the electric potential is plus 0.34 volts. Calculate the electric potential of the left-hand electrode in the diagram. Oh, left-hand electrode. Okay, so we need to understand what's being oxidized and what's being reduced here. This has a high concentration, and it wants to reduce that because we have a high concentration here, low concentration here. Equilibrium shifts so that to try and maintain that equilibrium. So what would happen here is that this concentration would reduce, so that this would increase technically, right? Because we want to reach some sort of equilibrium here. So this would undergo Cu. This would undergo to reduce this concentration. We need to go from Cu2 plus to Cu solid to reduce concentration of Cu2 plus, because really this is just Cu2 plus, right? Going to form, no, reduce it. Yeah, plus 2 electrons. No, to just form Cu solid. And then this would have to be oxidized to Cu2 plus. Yeah, to increase the concentration of Cu. This will be oxidized. This electrode here will be oxidized to Cu2 plus to increase the concentration here. So then the left electrode is the one that's being oxidized. So therefore, they want us to work out the left electrode, right? So it'll be 0.34 minus x equals 0.16. Therefore, x is equal to, if I move it over to this side, to be so 0.34 minus 0.16. That's just 0.18. I can see it from here. 0.18. Both electrodes contain a strip of copper metal in a solution that equals CO2 plus ions. Say why the left-hand electrode doesn't have an electric potential is plus 0.34 volts, because it's not under standard conditions of 1 mole per dm cubed of C2 plus ions. Square brackets represent concentration. Give the conventional representation of the cell in the diagram. Includes all state symbols. Okay, no problem. Just because I have space, I can just do that. Can make this AQ a bit more obvious. Hopefully this isn't too difficult to see why I'm doing this. When a voltmeter is replaced by a bulb, the AMF of the cell in the diagram decreases over time to 0 volts. So that's how the concentration of copper 2 ions in the left-hand electrode changes when the bulb is alight. Give one the reason why the EMF of the cell decreases to 0 volts. Okay, so this is to change concentration of copper in the left. It would increase because we're allowing the reaction to happen, right? A redox reaction to happen, so that would be getting oxidized. Yes, so it would increase. The concentration of C2 plus increases. Always write in full sentences. The reason why the EMF cell decreased to 0 volts because eventually the concentration of eventually equilibrium will be reached. How much time we've got left? 1 minute, 3 seconds. Eventually equilibrium is reached and the concentration of C2 plus ions in both half cells is equal. Both solutions become equal. Gotta hurry up now. How much time have I got left? 18 seconds. Okay. Which ion cannot catalyze the reaction between iodine and peroxidized sulfate? Can't do it. So between this and that. What is this? To get it just on time whilst explaining it, I'm actually quite happy with that. Yeah. By the way, the reason why this can't catalyze this reaction is because the reason why I could easily see that because this is bigger than this. I can clearly see that. And so this is going to be going in this direction. This is going to be going in this direction, right? And if that's the case, this electrical potential here is lower than this, than the I2. And therefore, it'll be going in this direction. Therefore, Cr3 plus, you could Cr2 plus could, but Cr3, sorry, which I cannot, sorry, I meant to say here that this Cr3 plus could, but Cr2 plus can't, right? Because this reaction would assume it's going in the backwards direction. Because you're trying to which catalyze between the oxidation, the reaction between this, right? So you want to oxidize. You want to oxidize I minus, right? You want to oxidize I minus. This is what you want. You want this backwards reaction to happen. And this Cr3 plus, right? or the Cr2 plus can't do it. Because it means you'd have to do the backwards reaction here. But that's not going to happen. This Cr3 plus here, this reaction wouldn't be able to happen because it has a lower electrode potential. Whereas all these other reactions would be able to do it, but wouldn't be able to do it. In my opinion, maybe I could be completely wrong, but in my opinion, that's what makes sense to me. Where you're trying to force this backwards reaction here. This backwards reaction can't happen at the same time, right? Lower electrode potential. Or maybe it could. I'm just trying to read it back now. Cr2 plus. Catalyze the reaction. Let's look at the mark scheme first, and then let me just go through the rest of the questions. I thought I was quite correct there, but I hadn't rushed it. Maybe I didn't. But if it looked so obvious to me at the time, but now I think by it may have been wrong. But I'm gonna go and try and answer this question now. So, I think I got them all from here. Okay. Question 5 is where I started off. So, salt bridge, complete the circuit. It says allow ions moving to allow free movement of ions. Yep, that's fine. Platinum, or you could say here to maintain charge balance, but it's only 1 mark, so I didn't think I needed to say that. Yeah, allow ions to flow, move, transfer, fine. Platinum there. HCl, 1 mole per team cubed. So to get M1, you need both of them in a row. You need to have H2 and 100 kilopascal, that's fine. M3 is FeCl2 and FeCl3, but it does allow, you can just say Fe2 plus and Fe3 plus. I can see it here on M3. And then 1 more per team cubed as well. And then the 4th mark is at any mention of 298 Kelvin, which I have here. It is 4 marks. Always read that, 4 marks. So 4 marks there. The equation, H2 plus 2, 2Fe3 plus H2. I know with the state symbols isn't really necessary, it's just ignore it, so it will be fine. Fe2 plus and 2H plus. Don't worry about the order of them, it's still the same thing really. If you start off with Fe3, 2Fe3 plus, or started off with plus H2, so it doesn't really matter. You can go H2 plus 2Fe3 plus goes to form 2H plus 2Fe2 plus, or it's the same thing as writing it 2Fe3 plus H2 goes to form 2Fe2 plus 2H plus. No problem there, you can already see what's going on there. I replaced the voltmeter, and then I said, yeah, actually word for word, actually, replace the voltmeter with a lamp. So, yeah, that's that. 2 marks. 2.3. I think that's pretty obvious. Now you get a mark for suitable scales. Yeah. I actually had the exact same ones, which makes sense because it's in the exact same proportion to give you 5 by 5 and then to get you to 1.16. So M2 here, M3, points plotted correctly, half a square, yeah. Half a square, yeah, that's off, so that's fine. Minus 0.013, that's the gradient. And then rearranging the equation, M2 and M1, so T is equal to whatever your M1 is over that, which I've done and represented here. And then answer of 302 or 303, that's fine. And it has to be at least 2 significant figures, that's quite important there. Minus 0.8. So I made a mistake here, right? So let's see why I made a mistake. So this is meant to be minus 0.8. So that's wrong. Minus 0.8. Okay, so that means that it would have been 0.33 minus x equals to 1.1, and then x is equal to 1.1, I assume. No, minus x equals to 1.1, minus 0.33, which would mean that minus x is equal to 0.83, and then x is equal to minus 0.83. But why is... Oh, the Zn2 plus. Zn2 plus is the one that's being... I am an idiot. I realize now. The one that's on this side is the one that's being oxidized. My bad, I made a massive mistake there. This is the one that's being oxidized. I switched them the wrong way around. I said this is the one that's being reduced, and that's the one that's being oxidized. See, you need to have a good understanding of your conventional representation. Don't make a mess up like I did. Yeah, this is why I always go for the mark scheme at the end. Again, I haven't done my A-levels since last year, so forgive me, guys. I'm just trying to help out. Yeah, so this is oxidation, and this would be reduction. And that simple mistake is what cost me the mark there. But as you can see, the same principle, same understanding of it would be the same here, right? But just obviously accompanying for that mistake. And that's how you got the minus 0.83. Yeah. Why is it 0.80 though? 0.33. Am I missing something out here? 0.33. What's the full electrode? But the electrode potential here from the graph is 1.1. Right, that's the y-intercept. That they represent the electric potential of a cell as being 1.1. And you said here 0.33. I haven't got an answer for you guys. I'm not gonna act like I do have an answer for you unless I'm missing something completely obvious. That's the gradient there. It can't be that. No, that's not it. This can't be minus 0.13 because that wouldn't make any sense. I assume that it's just meant to be 0.3 or something like, because I don't quite understand why it is why it wouldn't allow minus 0.83. But anyway, that's not marked there, lost. The Zn2 plus, so isn't understanding the conditions of 1 mole per dm cubed. Yeah, it's fine there. So in total from here, I got... I think I got everything right apart from that last part. So 16 marks, not bad there. I just tight guy. I should have. I don't revise these topics, man. I just go off the top of my head. I'm sorry, guys. 0.18. What was I? 7. It has mobile ions. Ions can move through it. It allows for the movement of ions between the half cells through the salt bridge. That's definitely a mark. 0.18 volts. Yes, that's definitely a mark. It's not understanding the conditions of 1 mole per dm. The concentration is not 1 mole per dm. It's not understanding the conditions of 1 mole per dm cubed, and the concentration is not 1 mole per dm cubed. I'd say the same thing, really. Yeah, because I'm saying that it's... Will they allow this? I mean, they're so edgy with their marking, but I've said here that it's not state the right, the left hand, because it's not understanding conditions of 1 mole per dm cubed. Yeah. If there's teachers out there that are saying that I'm being too generous with my marking, listen to your teacher. They're probably right. They're definitely more right than me. If I was being generous with my marking there, but I think that's pretty much the same thing as writing that, right? I try to be harsh, but not unrealistic in my opinion. But let's just keep going. D is correct. It's just a 1 mark there. The concentration of CO2 plus increases Eventually, equilibrium is reached. Concentration of CO2 plus ions in the two solutions becomes equal. Eventually, equilibrium is reached, and concentration of CO2 plus in both solutions becomes equal. Yeah, that's 6 marks there. Oh, that's technically yes. And then this is here is the answer is B. The answer was B. Now, try and get sorry. Why is it now? Because which ion cannot catalyze the reaction between iodide I minus between the reaction between this and this. Yes. Because that doesn't make any sense. That wouldn't make any sense. It would be Cr3 plus then in this case, right? No, because this reaction will want to go in the backwards reaction with I2. Yeah, if this was I2, Cr2 plus could work, I think, technically. But it's with I minus. That's why. It's with I minus. See, I made a quick mistake. I just went off the top of my gut because I had 23 seconds left. But I looked at the electrode potentials here. I said something wasn't right. And I said it's I minus here. And the Cr2 plus, why it would be going in the backwards direction, but it's trying to catalyze. This is already going. I understand my full process was that this is going in the forwards direction and this is going in the backwards direction. So why would you use this as well also going in the backwards direction? If this was because this would go in the backwards direction, right? This would go in the backwards direction if it was with I2. You could have used Cr2 plus if it's reacting with I2, but not if it's reacting with I minus. That doesn't work out. So Cr2 plus wouldn't work there. That's why it's B. Hopefully that works, and the next part of it will be going through the rest of these questions, but that is